Perfect, thanks. Okay, so let's conclude these lectures with some putting together geometry, dynamics, and so on, what we have seen so far. And this will probably be a little bit more chaotic than the previous ones, because I will necessarily skip some steps, because I do want to discuss a couple of questions that we said in the very beginning. So we had some big questions in the beginning. What happens when we go to factorization points? How do holographic directions emerge? And so on. And here I'm faced with an option of either going into many details and going through at the same pace as until now, and hopefully in a comprehensible way, or jumping a little bit, but then at the price of being able to at least give you a flavor of how can we start grasping these tough questions. Okay? So it's your role to try to slow me down in case I'm really overdoing it in terms of speed. Before we start, let me mention that at the end of the lecture I will mention some references, and I also wanted to advertise something that we run every year, which is called the Mathematica Summer School on Theoretical Physics, which is, I think, a very, very good physics school. So if you want, check it out. The deadline for applications is tomorrow, and the website is Mathematica Summer School Theoretical Physics, msssp.org. And it's run at Perimeter. It will be on entanglement. Juan will lecture, and so on. And the idea of the school is theory in the morning, problem solving with Mathematica in the afternoon. So if you want to see strong subadditivity proven in 2 lines in Mathematica, you should come. Very good. So let's see where we are. So our goal is to compute this expectation value of this Wilson loop, which is parameterized, say, the hexagon, for example, which is parameterized by these geometrical parameters, our space, our time, our space, and our angle, that is not seen here, which, as we said, we can think of these variables as taking this cusp, and tau would flatten it, sigma would move it left and right, and phi would move it out of the plane. And what is this object? This object is not the Wilson loop, because the Wilson loop perceives divergence because of ultraviolet divergences. But we consider some nice ratio. We use this middle square Wilson loop, the pentagons Wilson loops, to make a finite ratio. Okay? So this was one thing. Then we said that, by the way, these guys here, these lower objects here, they are all governed by a very simple property of the flux tube, the simplest one if you want, which you can think as the string tension or the energy density of the flux tube. Namely, as you take local operators and stretch them, their energy grows with logarithm of the spin times some function of the coupling, which you can think as the string tension, which is this cusp anomalous dimension that I wrote there. So much so that these Wilson loops that have no cross ratios, because they are just squares and pentagons, could be computed by just doing a computation in QED, just compute it in QED, glue one from one edge to the other, and replace your coupling by this cusp anomalous dimension. How do we find the cusp anomalous dimension? By going to this vacuum of my theory, which contains many, many, many derivatives. And going to this vacuum, we played yesterday with some example of doing exactly this, starting with an integrable theory. In the case we did yesterday, it was the ferromagnetic spin chain. And starting to put many, 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 many magnons and going to a very different state, very excited state, which was the antiferromagnetic state. So here we can do the same. And in this way, we can, and Benjamin Basu did it, because it's not as trivial as the antiferromagnetic case. It's more complicated. The theory is a bit more complicated, but it can be done. And here is the outcome of this analysis. Say we want to study one chromodynamic excitation of my flux tube. It's the analog of the Goldstone bosons that Raphael had. So we take our flux tube and we hit it with our finger, and some excitation is moving with some momentum p. This is the same as saying that I have some field strength moving in the sea of covariant derivatives in the language of operators, or I have a Wilson line and I put some adjoint field that moves in the Wilson line. What's the energy of this excitation? Well, the fundamental object is this matrix M that we wrote here. And the crucial thing is this -1 in this corner, the fact that we have to invert, which was exactly this statement that we went to a new vacuum, remember? So we invert this kernel to go to this new excited state. So what is this matrix? It is just, so there is some matrix here that, by the way, if we want to extract the element 1, 1, it doesn't matter, but later it will. So this matrix yesterday I did not write, I'm writing it today. But this is the important part. It's the identity plus twice, and then here is a matrix, very explicit, you see. just so that we don't even need to think much. Just J1, J1, J2, J1, J3, J1. See, just product of two Bessel functions. JA is J of 2GT. Okay, so this is the matrix, and you see the odd columns that are some minus, the even columns that are no minus. It's what it is. Okay, so we take this big matrix. This integral is a shorthand notation for this. It's integral dt over t, and then this exponential factor that makes it very convergent. And we compute this matrix, and for example, the cusp anomalous dimension is the element 1, 1 of this matrix. It's the simplest possible thing you could do with a matrix. You compute a matrix and you look at the corner. What about, for example, the energy of a gluon excitation on top of the flux tube? What about the momentum of a gluon excitation on top of the flux tube? It's not much more complicated. You see, you take the matrix, but now instead of extracting the element 1, 1, you first dot it with an infinite vector, and then you extract the element 1 of the corresponding vector. Yeah? So what is this matrix? This is this infinite matrix that is universal. It's universal because it has this physical meaning. We go to this vacuum. We always go there. So whatever we want to do, we will always go there. So this is universal. And then this is not universal because this corresponds to putting a gluon on my flux tube. But I could put a fermion or I could put a scalar, and this would change what these vectors are. So for each kind of excitation, there is a different vector kappa. For the momenta, the same. There is a kappa tilde. So you see the solution comes naturally in parametric form. It's not energy as function of p, but it's energy as function of u, p as function of u, and then you can invert and get energy as function of p if you want. Right? And what are these kappas? These kappas are some explicit vectors, and they are not much more complicated. So here is the u dependence in yellow. You see it appears inside some cosines and some sines, and otherwise it's a bunch of Bessel functions once again. And just for total completeness, I thought I should do it once. I never did it before. But here is the S matrix also for two gluons written with all possible factors at any value of the coupling. This is how two gluons scatter with each other. Okay? So there are some gamma functions. 3 gamma functions divided by the same thing with u and v exchanged. Here's some exponential that is totally explicit. Something with u minus something with v. And here, you see kappa dot with m dot with kappa. So this is the most general thing you could do with a matrix M. Either just extract an element, dot with a vector and then extract an element, or dot with two vectors. Right? So this is the most general case here. It's a bit more complicated. And this gives a dependence on u and v. And you see by construction it is antisymmetric. If I swap u and v, I get 1 over the S matrix, which is just unitarity. Okay? Good. So now I did not prove this. Again, I think conceptually it's not more complicated. Once you know the bit equations, it's not more complicated than the antiferromagnetic case, conceptually. Technically it is. And also to get bit equations, it's a bit more complicated in n equals 4 than in the XXX spin chain. But it can also be done, and there are many reviews on the subject that I can give you later. But you can agree that there is some notion of spin chain. I'm telling you that the excitations are integrable. I think you can believe me. It's not a big mystery. Any question on these results, on the notation? So let's see what happens at weak coupling. Okay. Now at weak coupling, when g is much smaller than 1, remember that g and lambda are the same basically. So what happens as the coupling is very, very small? So as the coupling is very small, it's important to note that most things simplify dramatically, because these Bessel functions, they all start with g to the power a, so they are all super, super small. So everything you can see, almost everything is super small, and you can drop almost everything. So when you go to very, very weak coupling, you basically keep this identity. And roughly, that's the leading order thing. You just keep the identity and nothing else. And then, once you want to go first loop correction, you keep the J1, J1, because J1, J1 is G squared. This is G cubed, this is G cubed, this is G4. You keep the corner one. Then if you want to do 3 and 4 loops, you start keeping the other ones. But it grows very, very slowly with loop order for the matrix M. Similarly, for these vectors kappa, the further you go down, the higher, the more they are suppressed in the coupling. This one here is probably J7. It's already very suppressed. It's like G to the 7. Okay? So it's very, very easy to compute. So let me write to you what this is. So if we see, so to leading order, of course, the energy is just 1 plus g squared times something. I'm going to write in a minute. You see, it's the 1 there. And the momentum is 2u plus something. The momentum I'm not going to write. And the energy, if you compute this object, it's you get this. Up to 2 loops plus order g to the 4. Okay? Where psi is the log derivative of the gamma function. Okay? So what is epsilon of p? Well, it's trivial. Just replace u by p over 2. At this loop order, it's not very complicated. Right? Okay, very good. And what about the S matrix? Two leading order, F, F, U, and V. Can someone tell me what should I take out of those lines? That expression there, what should I take out of for the S matrix? There are 3 lines. What should I do with those 3 lines if I want leading order? Well, you see, these kappas, they are small, right? So this is small. So this kappa kappa, this is small. This is like g squared or something. So this I don't care. This line I don't care. It's good. The complicated line I drop. This one I also don't care. I have j0 minus 1. j0 is the only Bessel function that goes to 1, but you subtract 1. So this is also like g squared. I also don't care about this line. So it is just the gamma function part. So with coupling, it is just the gammas. So it's gamma, gamma, gamma. So let me just be schematic because we have the gammas there. Gamma, gamma, gamma. Gamma, gamma, gamma plus order g squared. So here is how gluons behave at weak coupling. Okay. What about strong coupling? Now this is the beauty of this. As Joan said, we have these examples where we can interpolate and go from weak to strong coupling and so on. So what about G much bigger than 1? Well, we can compute, but now it's much harder to compute. As I told you, I mean, it's already a bit trickier. I mean, everything is well defined in the blackboard, but it's a mathematically more complicated problem. So let me tell you what the result is. Let me write just epsilon f as function of p directly, and it's square root of 2 plus p squared. And the S matrix between two gluons with momentum p and p prime is 1. Okay? So the gluons become approximately free, okay, which is in line with this intuition of Damas-Goldstone boson. So they're at strong coupling, these are modes of ADS, and there is some kinetic term and some interaction, and the interaction leads to an S matrix, which is 1 over square root lambda. Otherwise, this is just a kinetic term. The S matrix starts with 1. And this is the dispersion relation of two modes of a string. You stretch the string, and you consider two ripples on the string, which become just relativistic ripples that move on the string. So we get a relativistic particle. So this becomes a relativistic excitation of mass square root of 2. And you can now cross your fingers and ask, you go to string theory, you take your string action, you put a big folded string rotating in ADS, which should be the analog of these flux tubes. You put a big folded string, and you write x equal x classical plus delta x, and you expand the string action. And you go and see the mass of the fluctuations. And indeed, you find two fluctuations of mass square root of 2. Why 2? Because we have gluons of positive and negative helicity. So it should be exactly 2. Okay? So this is beautiful in the sense that this indeed agrees with the two modes of the string. Of two of them. There are more modes of the string. We'll discuss them in due time. But there are two modes which have mass square root of 2. Well, you see, it's non-trivial. For example, for the S matrix, it's quite clear that this expansion is non-trivial. You see, what I'm saying is that at strong coupling, all these lines conspire to get rid of these gamma functions. So it clearly cannot be a totally trivial way analysis of these functions, but it's what it is. Good. You see that everything is very explicit. So basically, the claim is as follows. We can write an explicit expression for Wilson loops at any value of the coupling in n equals 4 super Young Mills. And let me tell you schematic, or not even very schematic, let me tell you what it is. Okay, maybe before. No, I think it's a bit early. So, bit early. So yes, good. No, it's in the planar limit. This is all in the planar limit. You have no signs of the duality. As duality is not planar. Yes. A bunch of. There are. Very good. So, what does it mean when you have poles in an S matrix? Typical in 2 dimensions, it means that you have poles, that you have bound states. So you could have bound states or not. So let's see. Yeah, this lecture should be more like discussion. Ask me lots of questions because I have no notes or anything. So if you just help me and guide me through, it's awesome. Okay, very good. So let's see what poles of an S matrix or zeros of an S matrix are. So for that, let's write a 2-particle wave function that we had yesterday. So the 2-particle wave function is e to the I p1 position 1 plus I p2 position 2 plus the S matrix that depends on p1 and p2 times e to the I p2 and 1 plus I p1 and 2. So this is the wave function for 2 particles. Okay, it could be, for example, our 2 Fs. Okay? And then I ask myself, can the momenta, can P1 be complex? And of course, it should be the complex conjugate of P2 in that case, so that the total momenta is real. What would this mean? Well, if the momenta are real, so let's say this is the wave function for n2 bigger than n1. The particles are indistinguishable, so we just write the wave function in one chamber. So this is the wave function when n2 is very big, when n2 is bigger than n1. So if P2 has a positive imaginary part, it's okay. This term is okay. Okay? So if imaginary part of P2 is bigger than 0, then when n2 is very big, this is exponentially suppressed. And then the imaginary part of P1 would be smaller than 0, so when n1 is very negative, this would also be suppressed. Right? So this would be good for the first exponential. This is good for the first exponential. But what about the second exponential? It will be a disaster. For the second exponential, now this term explodes and this explodes as well. So what's the way out? Well, we can have this complex solution if the S matrix vanishes at that point. Okay? So can and the answer is yes if the S matrix at the value P1 and P2 is equal to 0. Okay? And similarly, if I do the analysis with opposite signs, in that case I want to keep this term versus that one, so I want this one to have a pole, which means that this is much bigger than that. But what matters is the relative term. In other words, zeros and poles of the S matrix, if in the appropriate place, are what tell you if you can or cannot form bound states. Okay? So it's a dynamical question. We compute the S matrices of all these particles and then go and ask ourselves, are the poles of these S matrices in the place that allow us to form bound states or not? Okay? And this we can do for all the particles of the theory. We can take gluons and check. We can take scalars and check. We can take fermions and check. And once we are done with checking these things, we have the full spectrum of fundamental particles of my flux tube, namely all the fundamental particles and their bound states. So let me tell you what the summary of that gives. What are all the fundamental particles of the n equals 4 flux tube? Okay? So here is the outcome of looking for bound states. Very good. So what are the excitations? Let me write them. So we have a scalar. We have scalars, fermions, and gluons. Fermion bars and gluon bars. Okay? Is it okay, this notation? That's gluon of positive helicity, gluon of negative helicity. And now you ask, they do they form bound states? And the answer is gluons do. Indeed, these poles of the S matrix are such that they form bound states. So as there is a bound state of 2 gluons, a bound state of 3 gluons, a bound state of 4 gluons, and so on and so forth. And here I can have a bound state of 2 gluons of negative helicity, a bound state, and so on. What about scalars? No, they don't form bound states. Fermions, they don't form bound states. This is a dynamical outcome of the analysis. It doesn't have a geometrical explanation as far as I know. Okay? And what am I drawing? Why am I drawing it in this way? What is special about these columns? Let's think a little bit. So here I can think that from the point of view of SU4 representations, this is a singlet of SU4. Here this line, this fermion, it transforms in the 4 of SU4. Scalars transform in the vector of SU4. Psi bars in the 4 bar of SU4. And F bars are again singlets of SU4. Right? They have no indices. Right? Psi has an index A, upstairs or downstairs, depending if it's fermion or antifermion. And scalar has 2 indices down, phi AB. Right? And these lines here that I'm drawing diagonally, these lines here, let's see, all this here, that is being drawn diagonal, is the twist. Sorry, I'm writing in the black hole region, but I will try to write very big. This is the twist of the excitation, which is the energy conjugated to tau. So all these guys have energy 1, F, psi, phi, psi bar, and phi, which is just you put one field and it has dimension 1. These guys here, in this column here, which you see there's only one field, has twist 2. And this column here has twist 2 as well. So twist increases diagonally like this. Okay? And what about the vertical lines? The vertical lines, perhaps it's time finally to use a different color. The vertical lines represent the helicity of these excitations. Remember that we said that we have an angle phi that appears multiplying the angular momentum of my excitations, right? So we have this angle phi. So gluons will have helicity 1. So these guys will have helicity. Where should I write? I will write this outcome, and put here up here. So these guys, like here, have m equals 0. M is what multiplies phi. The gluon, for example, has m equal 1. Gluon bar has helicity minus 1. And fermions have 1/2. M equal 1/2, this guy. And minus 1/2, this one. Okay? So this is the helicity, vertically. Starting, this is twist 1. They are the lightest excitations. And then, as we go far, it's the heavier ones. And these columns here are the SU4 representation under which they transform. So this is the particle content of the flux tube of n equals 4. Yes? Good. So this has helicity 1. Can you guess what this one has? 2. Good. This has helicity 2. And you ask me, can a gluon of positive helicity form a bound state with a gluon of negative helicity? They don't. The force is just not attractive. They just don't. If you study the S matrix between these two guys, you see that they don't form a bound state. Okay? So gluons, you see, that's why I have F, F square, F cube, and here I have F bar square, F bar cube. I'm not writing F times F bar or anything like that. Okay? So there are all these helicities and all these particles and so on. No, this is the classical one. Sorry, classical one. Small lambda. With kappa. So this is just, sorry. This is the twist. at G equals 0 without any anomalous correction. Otherwise, it is the energy that we were writing all these finite coupling expressions. So it's when we put the coupling to 0. You see this 1 is the one that I put there. Epsilon equal 1 plus 4G times something. That 1 there is the twist one. Okay? What is the mass of the helicity 2 bound state? It's 2 square root of 2. Okay? Good. So your colleague is asking what happens if we study the same excitations if we follow the mass of the other excitations. So given that you ask, let's do that. Okay? Please keep asking questions. So let's plot the mass of the various excitations. What are these excitations? What is the mass of an excitation if the theory is not relativistic? Is the energy when the particle is stopped. So by this I mean energy of a given excitation when the momentum of the excitation is equal to 0. And we plot it as a function of the coupling. As we said, they all start with 1. Okay, they all start with 1, the fundamental ones, these twist 1 guys. And then what happens is the following. We have fermions that because of supersymmetry, they stay at 1 completely. Because supersymmetry is broken by this flux tube, it so turns out that fermions at 0 momenta are Goldsteinos of this broken supersymmetry, and their mass cannot be corrected by symmetry. Okay? So the fact that this line is flat is an artifact of SUSY. A fact of these guys being symmetry generators of a broken supersymmetry at 0 momenta. So the fermions always have mass 1. And at strong coupling, they become relativistic fermions of mass 1. And that's good. You go to the string action, you expand now the super string action around this folded string, and you see that you get fermions of mass 1. So you are happy. Okay? So this is good. This is for the fermions. The gluon, as we said, it goes, and for the gluons, it goes to this square root of 2. Okay? The bound state of gluon that starts at 2, see this, okay, this is not twice this, it should be. That is 2 goes to 2 square root of 2. Okay? This would be the bound state of gluon, F squared. Okay? What about, and this guy you don't see in string theory as a fundamental mode, but you see it rather as a very, very weakly coupled bound state of 2 fundamental string modes, which is okay. They are a bound state, and indeed their binding energy becomes very small, and you see that strong coupling by just putting 2 modes of mass square root of 2 on top of each other. That's how you see the bound state. It's not a fundamental polarization of the string. Okay? It's exactly the same. It's exactly twice. It's exactly twice, which is the statement that the binding energy of these bound states goes to 0 at strong coupling. Okay? It's all at intermediate coupling. That's a good question. I'm not positive. No, at intermediate coupling, I'm positive. At intermediate coupling, of course, it's a bound state. So at intermediate coupling, here, I don't know if this picture reflects that or the opposite, the energy of an F square is smaller than the epsilon of 2 Fs, where they have P1 and P2 that add up to P. This is the statement of being a bound state. But at strong coupling, it becomes saturated. Is the picture correct or not? Probably not. I suspect the concavity should be different. Okay, good. Doesn't matter. You understand what I want to draw. And then we have scalars. They start with 1. And scalars go to 0, the mass of the scalars. And it vanishes as e to the minus square root lambda over 4. It vanishes exponentially fast. And there is some nice physics about this, which I hope I have time to tell you about. All I want to point out is that this spectrum is something we can plot. We just compute the expressions we said in Mathematica and we just plot them. But you see that supersymmetry is broken. There's no supersymmetry. All the modes have different mass. We start at weak coupling where everything is degenerate, and then everyone has a different spectrum. So at finite coupling, this is consistent with the idea that we have a big flux tube. Flux tube is a tube of energy with a million of gluons. Of course, it breaks supersymmetry. I mean, it's a very, very bosonic background. Okay. Any question? So now that we know all these excitations, I can do here the claim. The claim is the following. That's the main claim here. The claim is that we can compute this Filson loop at any value of the coupling as follows. We do the following. We say that we will sum over all possible flux tube excitations, right? All possible flux tubes that are stretching here between this quark and this antiquark. You see, you have this flux tube that stretches between the quark and the antiquark, and we sum over all possible states. Yes? No. So, it's no. So we have a flux tube, and we want to sum over the states. What does it mean? We sum over the states. What's the slightest state? Vacuum. What's the first state? One gluon. Second state, two gluons, and so on. So we have to sum over all possible states. So what we do is we go to the table that I wrote there, and we take any number of particles out of this table. Right? We start taking multi-particle states made out of any possible excitation here in this table. Okay? I start with vacuum, then I put one gluon, then a bound state of gluons, then two gluons. Right? Can I put a scalar? Can I put one scalar? Can I sum over the state with one scalar on my flux tube? So I start with my Wilson loop, and then in the middle there is one scalar flowing. Is it possible? Many people are nodding no, but no one is saying it or explaining it. Why it's true that you cannot? Why? So I start with my bosonic Wilson loop, my gauge field around, and I sum over what is flowing. Why can't I have a single scalar going up? Sorry? Symmetry. What symmetry? SU4, because a scalar is not a singlet of SU4. A scalar transform is in the vector representation. I cannot start with something that has no SU4 charge and start producing stuff with charge. Can I have three scalars? See, I almost tricked myself. Can I have three scalars? No, because with three scalars I cannot form a singlet with three vectors. What about two scalars? Yes, with two scalars I can put the phi I, contract the indices. This is a singlet. Very good. So I sum over all possible kinds of excitations. Let me put a vector A. A vector A indicates, for example, A can be, for example, let's do an example. It can be a gluon. It can be a bound state of a gluon of negative velicity. And it can be, as we said, about two scalars. So this could be a singlet. Of course, this is not the simplest case. The simplest case is just one gluon or even the vacuum. We sum over all possible A's. And these guys, each of these objects, comes with its own rapidity, with its own momentum parameterized by this U. U1, U2, up to U capital N. Then what do? We integrate over its momenta. du1, dun. And then we have some integrand. Let's use the kind of letters that Freddy was using. We have some integrand I. And what is the claim? What do we know about this integrand? What's the claim? Okay. The claim is that this integral contains two factors. One, it's not a claim. It's from symmetry. It must be true. It contains e to the minus tau times the energy of my state, which is a sum from j equal 1 up to n of my energies of my particles. Right? That was the big payoff of introducing these nice variables. We know what to write now. Plus I times sigma times the sum from j equal 1 up to n of the momentum of my particles. Plus I times the angle phi times the sum of the helicity mi of my particles. Mi I read from the table, and p and epsilon I compute from expressions like the ones I wrote. Right? And what's the weight that comes with each Boltzmann weight? The weight is what is the probability of starting with a vacuum here in the bottom and producing that state psi in the middle that then annihilates back to the vacuum here. So the claim is that then what multiplies this is a product of two objects that we call the pentagon transition that goes from 0 to the state with u1 up to un times the pentagon transition that goes from u1 up to un to 0. And to integrate over these rapidities, it's useful, even though we could absorb it in the piece, to have some integration measure, mu of u1, mu of un. And this, of course, depends on what kind of particles I'm producing. Similarly here also, particle A1, particle AN. Okay? Times. This is not a big claim. I think this is mostly just conformal symmetry that implies this, plus the fact that it's integrable. But the claim is that these objects can be found and can be written explicit in terms of this matrix M and these vectors kappa and kappa tilde. In other words, they are observables of the n equals 4 flux tube. They are as good as the energy and the momentum. These measures and these pentagons, as we said, this pentagon that has no cross ratio is a property of the flux tube, like the energy is. So it's not so surprising that like the energy and the momentum, we can just write them down explicitly. Okay? So this is the form of the solution. Now, there is still a sum, an infinite sum, but the point is that if I truncate this sum up to states where this vector A has 10 fields, for example, suppose this A has 10 fields, well, then the energy is at least 10 plus something small. This is at least suppressed e to the minus 10 tau. If tau is 2, it's e to the minus 20. It's already very small. I don't need the first 100 particles. So I can truncate this sum fairly early if I want to get very good numerical results. Which is the usual thing, that if I want to get energies up to some, if I want to study physics, unless I'm considering very, very ultraviolet processes. If I want to study some physics at some distance, reasonable distance, tau, only the lowest energies matter. Okay? So the claim is that with this expression at hand, and I'm going to give you an idea on how we find these objects now, but the main claim is that now that we have this expression, we can start asking the kind of questions that I said in the beginning. So here we have a representation of the amplitude. How do we start extracting physics out of it and study particular interesting kinematical regimes? What happens when I stretch tau a lot, when I send sigma to particular values, and so on? What is going to happen? And we are going to try to start seeing how come this representation indeed provides some answers for this kind of questions. Okay? So this should not be totally surprised again. This P, we managed to find the S matrix and so on. And basically, now we have to find these pentagon objects and these mu's here. Okay. Any question here? Mu is some integration measure. I could put it close to the integration d mu1 over d mu n. Yeah, I wrote du1, dun. For each u, there is kind of a measure. It's du1 times mu1. It's a measure. It's a function of just the rapidity u1 up to un. You see, it's a totally factorized term, and I can associate it to the measure of integration. But okay, that's a good question. So let's try to understand what is measure, where it comes from. As I said, I do prefer if you would ask me lots of questions today. So let's try to study what this Wilson loop would be. Yeah, let's do the following. Before trying to understand, let's see if we are just totally crazy. Let's see, can this be just totally wrong and we are just hand waving and saying, oh, we have this flux tube and so on. So let's do an experiment. So we go and do an experiment. So what is the experiment? We compute this Wilson loop explicitly for the hexagon at one loop. We ask someone to compute this at one loop. So this is very simple. It is just you draw a propagator between each possible edge from one edge to the other of these diagrams, and you compute this ratio. Okay? Okay, so you do it, and you get g squared times pi squared over 6 plus Li2, 1 minus u1. I don't remember. It can be actually already be wrong, but I think maybe it's not. Okay? No, I forgot one more term, so there are 6 terms. It's not important. Okay, some signs here are wrong, but no one cares about the explicit expression. Okay, very good. So this is what the result looks like. You see, people don't write it in terms of this tau, sigma, and phi. They write it in terms of cross ratios, u1, u2, and u3. Right? This is the most reasonable thing, indeed. So now what do we do? What we do is we plug the expressions we got before. Okay, let me remind you, for example, what was u2? u2 was 1 over 1 plus e to the 2 tau. And u3 and u1 were slightly more complicated. We plug it here. So we plug this, u1 and u3. We plug it here, and we expand at large tau. We series expand this at large tau, and we see what we get. Is it reasonable? Do we start seeing things that can look like they have this kind of interpretation or not? Or are we just insane? Okay? And the Wilson loop is, of course, 1 plus Wilson loop at one loop plus ... Okay, very good. What do we expect to get? What we expect to get is not trivial. It doesn't need to work. It could fail even before any explicit expressions. It's not totally obvious that this will work. Because we have a function of 3 variables, but we are saying that its expansion is very special. When I expand at large tau, I get exponentials of minus tau, exponential of minus 2 tau, exponential of minus 3 tau. But each power of exponential of n tau tells me that I have a state with energy n. Then I have to take states out of this table for a given twist, and I know what's the maximal helicity that they can have. So the expansion in tau and in helicity are correlated, and I must get something very, very particular. I cannot get anything random out of this. So what do I expect to get out of the generic expansion of the Wilson loop at weak coupling? what do we expect to get? What should we get? We should get Wilson loop to be 1. 1 would be the vacuum, plus e to the minus tau. This would be a gluon or an anti-gluon, right? And because it's a gluon or an anti-gluon, sorry, a gluon, a positive velocity or negative velocity, they should come with e to the I phi or e to the minus I phi, and we should not distinguish, so there should be some kind of cosine phi. And then some momentum p times sigma that we are computing, where we have f of sigma, which would be the integral of some f hat of p e to the I p sigma. But what we see when we expand the function is this. So, right? And then what do we expect when we compute e to the minus 2 tau, the next term? Well, we can have cosine of 2 phi times some function f tilde of sigma plus a function g tilde of sigma plus dot dot dot. You see, it's already a very particular kind of expansion. Why did I write these terms? Let's see. What is cosine of 2 phi? It's terms that have helicity 2 and twist 2. What could they be out of that table? Good. So this f tilde, so this f is just from this. Now f tilde could get contribution from f square or from 2f's. It can be a bound state or just 2f's. And the same thing for f bars. They have maximal helicity. If it's maximal helicity, I don't need to mix it with anything else. What about g tilde? G tilde could get contribution from an f and an f bar. This would have total helicity 0. Also, 2 scalars. This would have total helicity 0 as well. Or 2 fermions, namely a fermion and a fermion bar. They would also have, they could also form a singlet, and they would also have helicity 0. Right? And so on. So you see, it's already non-trivial. I could start expanding and getting, for example, e to the minus tau times a complicated function of sigma and phi, where phi doesn't show up outside, and it just becomes totally entangled with sigma and appears some function 1 over e to the sigma plus e to the phi downstairs. And this would immediately tell me all this picture doesn't make any sense. So it is kind of a sanity check. And indeed, it works. Okay. So indeed, whatever we write, which is what we expect, we compare with the expansion of this function to 100 terms, and it all comes out exactly as we expect. And for example, this f of sigma is given by 2 sinh sigma times sigma minus 2 cos sigma times log of 2 cos sigma. Okay? I don't remember this sign. And then we Fourier transform. We Fourier transform this expression, and this gives integral du over 2 pi e to the 2I u sigma. So I'm Fourier transforming but putting a 2 here, which is fine. Why do I do it? Because I know that the momentum of my excitation is 2u, remember? So it's useful to do it with this convention. And then here I get, let me call it mu of u, where this mu of u is pi over cos of pi u times u squared plus 1/4. Okay? So for now, let's keep it as this. Okay. So it does seem to make sense. So what should be the interpretation of this term according to our explanation there? This is one gluon, right? So it is one gluon. So let's reduce this to one gluon. So we have n equal 1. So we have energy, which is 1. So it's 1. It just got out of the integral. We have m, which is plus minus 1. It got out of the integral. It's the cosine phi. Okay? Let's put 2 cosines such that it's the sum of 2 exponentials without anything else. Then there is e to the I sigma p, which is this e to the 2iu. So this mu of u is the integrand, is the remaining part of the integrand, the second lines, right? This mu of u is the bottom part. So what is this mu of u that we are computing here in that notation? The mu of u in this blackboard, so here, is equal to the probability of creating a gluon from the vacuum times the probability of annihilating the gluon into the vacuum times what we were calling the measure of the gluon. Okay. Now, here I have some normalization freedom of setting the probability of creating a gluon to 1, because I can always normalize my states. When I say I have a probability of creating a given wave function u, if I multiply this by 2, it rescales by 2. So what matters is the full integrand, but what I can say is that I will normalize these guys, I will set them to 1 for a single excitation. And then what we just computed here was an experimental determination of what we were calling the measure before, this mu, at leading order in perturbation theory. Okay? So this mu is just the mu that I had there. Okay? Now, how do we see where this mu would come about in a more geometric way? It's also easy to see more geometrically. And it's the analog of saying that a 3-point function is well defined when I normalize the 2-point functions to 1. Otherwise, it's not well defined. And this mu is very much the analog. It's the statement that the pentagons, for them to make sense, if I want to change the normalization of my flux tube states, it better be that the 2-point function of the flux tube states is normalized. Okay? So let's see how we would see this coming about. So let's suppose I want to study my Wilson loop, which starts with 1 plus a single particle flowing on my flux tube. Okay? Which is what we are doing here. Now, a single particle flowing on my flux tube, what did we say it was? We said it was, we think of this as 2 pentagons, right? And we said that this picture, we think of this picture here, where we have just a single gluon flowing. We said that this is a pentagon, a probability of pentagon when I put an F up here. This is the first part. I create from vacuum, I create an F, times the pentagon, where an F goes to the vacuum, right? Do you agree? This is what we said. 0 goes to F, and then F goes to the vacuum, these 2 pentagons. You see that the way we are gluing, we are tessellating these pentagons, is more like we are putting some tiles on top of each other, but they overlap. Right? This square is counted twice. This square appears here, and it appears here. So it looks like we are overcounting. It looks like we are saying we are studying the propagation, and we are overcounting this. So if we would like to remove this overcounting, what we should do is divide by this square, where I put an F at the bottom and an F at the top. Okay? And this is exactly the 3 building blocks. It's probability of creating an F, probability of annihilating an F, and this mu, which is the inverse of this square. So this square is just 1 over mu. Okay? And how would I construct it? Is it a new object compared to the pentagon, or can I say the pentagon is the fundamental object and the measure is derived from the pentagon? And indeed, this is the answer. So let me tell you why. So this is actually derivable from the pentagons. And the point is that if the particles on the pentagon are very far away from the idea is the following. Suppose I start with a pentagon where I put an excitation at the top with some rapidity u, v, and some particle at the bottom with some impurity u. Right? Now remember, what is this u and v? They are related to the momentum. Momentum conjugated to sigma, and sigma is a symmetry of a square. Right? Which square? Well, this pentagon, as we said, is divided into squares. And I can move this excitation down here with the symmetries of this square, and move the excitation here with the symmetries of the top square. Right? Do you agree? So this variable u is conjugated to a sigma in the bottom, and this variable v is conjugated to a sigma at the top. Okay? And what I can do is I can send both these particles very much to the left. Way to the left. When I do it conformally, from a conformal point of view, this is equivalent to keeping them at the same position, but instead flattening a lot this edge so that it approaches a square. From a conformal point of view, either I send them here, which means send them to sigma equal minus infinity, or keep them here and flatten a lot this. In other words, as they go to the left, they don't see the cusp anymore. They just see a square. They think they are on a square. And when you go back to Fourier and you translate what this means, this translates into saying that the measure, or the inverse of the measure, is just the residue when u equal to v of the transition of a particle from u to v. Okay? Okay. So then, the big question is, of course, how to find this piece, at any coupling. Right? Because if we do, this is the remaining building block. Energies, we are done. Momenta, we are done. Elicities, we are done. Measure, if we find P, we relate it to the measure. So all we have to do is find these pentagon transitions. Okay. And the basic idea, the main idea, if you don't want to work, you use the bootstrap. Right? Bootstrap is this idea that you pull yourself by your straps and you find a set of symmetry properties of these axioms, you constrain them so much that they come out for free. Okay? And the idea is to bootstrap them. So what does it mean? How do we bootstrap these pentagons? What exactly do I mean by this? Well, let's try to see what properties should they satisfy. So let's specialize, let's consider A to be a set of gluons F, A1, F, AN, where AJ being positive means positive helicity, and if it's negative, it means negative helicity. So F minus 1 is F bar, just to have a unified notation to describe all gluons at the same time. And let's study pentagons that involve gluons going to gluons, or just gluons. Okay? So this is a particular case of this. So we want to study what's the pentagon for a given set of gluons, the probability for producing a given set of gluons, A1 up to AN. Okay. Which this object, that how do I picture it? I draw a pentagon and I put some particles here, U1 up to UN. right? This is what this is. This is just a Wilson loop with some excitations in the top. By the way, just to make the logic more tight, let's go back to, let's keep that definition in mind and go back here. And say, okay, here we have a Wilson loop with some insertion here. But this is divergent, right? This is divergent. If I try to do this, suppose I just try to do this. This is divergent. There are divergences here, right? And then I say it's this times this. This is also divergent. There are divergences here. And I have to divide by this overcounting. But this is also divergent. What exactly do you mean? Everything is divergent here. But now you say, oh well, if all this is divergent, let me divide this object by the same thing without insertion that cancels these divergences. So I say, let me take this, and to make it all well defined, let me divide by the same without f. So this is supposing I start with a straight W, the usual Wilson loop. And then what would I conclude just by this? I would say, let me divide by this without f, so that I cancel these divergences, and I would arrive at the definition for mathcal W that we said in the beginning. This natural definition of dividing by these pentagons and so on. It would be the natural thing to do if I would like to start regularizing the blocks. You would not have to think and to guess this definition of this cal W as this particular ratio. Okay. So we want to bootstrap this object, where of course by this object I mean this divided by the same thing without insertions. And what we do is we start writing some axioms that this object should satisfy. For example, we say that this object should be the same as the S matrix that flips particle 1 and 2 of U1, U2 times the same pentagon transition where I swap A1 and A2. Which graphically, I just say that this picture is equal. It's like a Schwinger-Dyson equation. I just take an S matrix and then I put U2, U1. Right? S matrix times the same object. Swapping two particles, you pay an S matrix. This is an axiom. You see, it's non-trivial because this S matrix was a complicated function at all loop orders. So now I know I have to find a function which has this symmetry property. I swap two arguments and I pay this complicated function of the coupling, this S matrix. So it's a powerful constraint on this P. Another constraint comes as follows. There exists an analytic continuation U gamma. This means you take U across a path gamma. It can be, it actually amounts to coming back to itself, but after doing some monodromies in the complex plane. The point is that there exists such transformation where the energy after the analytic continuation becomes I times the momentum, and the momentum after this analytic continuation becomes I times the energy. Okay? This transformation, it's not totally trivial to find, but you can just take the expressions for the energy and momenta that I wrote, and you could in principle look for such analytic continuation which as functions would flip energy and momentum. And why do they need to exist? Because what is this? This is implementing a weak rotation, a rotation by 90 degrees. But the square is invariant under rotations of 90 degrees. Right? A square, I can put excitations in the bottom or I can put excitations in the side. It's totally invariant. So my theory, when I describe propagations in this square, should have this mirror symmetry. It should be possible to rotate excitations and weak rotate them around. Okay? So this has to exist because the square, I can put an excitation here and apply some transformation that weak rotates the excitation such that if I put the particle an F with some U gamma, it amounts to putting an F with some U. Okay? Is it okay? Do you agree that such thing has to exist? Yeah? Now, what is not clear from this argument is if after continuing, is it F or is it F bar? Because F and F bar is measuring the helicity, and after rotating, it can be that it changes. So this you can do by looking at the symmetry matrix that I told you with tau, sigma, and phi, and asking, if I relabel all the edges and I see the particle from another point of view, is phi going to phi or phi going to minus phi? And the answer is phi goes to minus phi. So the proper way to think is that F goes to F bar. Okay? That is just an outcome of analyzing carefully this symmetry of the square that I told you about. So now we can write a very powerful axiom, which is as follows. We just say that we can apply 5 mirror rotations to take particles around this object. Okay? So now we don't apply this transformation once to move it by one step, but we apply it 5 times such that we can write an axiom such that we can write the axiom. We can say, for example, that you take a pentagon with gluons A1, A2, tac, 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 AN, okay, which is that picture there. And let's take U1 and apply 5 mirror transformations, 5 such analytic continuations, and then U2 up to UN. What happens? U1 goes all the way around the world and comes back on the other side. So now it becomes P, where the arguments are U2 dot 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 UN, and U1 is at the end. What about the indices? A2 ta 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 AN. And now there is a small subtlety here. Can someone point out? A1 bar, which means in this notation minus A1. Why minus? Because each time we do a step, we change F to F bar, F to F bar, F to F bar, and we did it 5 times. So in total, we start with a gluon, say, of positive helicity, and when it goes all the way around the world through a sequence of 5 mirror transformations, it ends up, well, it starts to the left, now it ends up on the right, but because it did 5 transformations, each time it changes from F to F bar, it changes its helicity, so we end up with this. So we write down such axioms. This axiom is also non-trivial because this U gamma, this gamma transformation turns out to be a very funny transformation, which is as follows. It so happens that these functions, they have cuts in the complex plane of U. And where are these cuts? These cuts are at position minus twice the coupling minus I over 2, twice the coupling minus I over 2, and the complex conjugate. So minus twice the coupling plus I over 2, twice the coupling plus I over 2. And this analytic continuation, gamma, is the following. You take a point, and you go through these cuts, and you come back. Okay? But you see something funny. Suppose someone gives you an expansion in perturbation theory. In perturbation theory, these guys disappear. Puck, they collapse. Because these cuts have size 2G or 4G. So when G goes to 0, they close. Right? So it's like you have to pass a door before it closes. Right? But the door is closing, and you need to do it at finite coupling. You need to solve the theory at finite coupling, and then you can take the coupling to 0. If you first solve the theory in perturbation theory, you don't see cuts. The cut's closed, and you can still see there is a door there. How does it manifest itself? In poles. Instead of having cuts, you close and you have some poles. And as you stretch a bit, you see that instead of a pole, it's 1 over square root of U minus A prime, where A and A prime are very close. So these poles of the S matrix that we were seeing there, for example, they are cuts that closed, and we were seeing them as poles. So this is a funny, so you see that coupling is being injected in 2 very direct ways. One, this analytic continuation needs to be done at finite coupling. And second, this S matrix. You need to compute it at finite coupling. So such axioms, and I could write 2 more axioms, are quite powerful, but you get the feeling. You write some axioms, and the basic idea, you write some axioms, and then you solve the axioms. Okay? And you solve these axioms, and you get the solution for these pentagons, and then you get the Wilson loop at finite coupling. Okay? So this is the basic idea, and there are many small details that I'm not telling you here, how to deal with the indices of scalars, Do we really understand this well for all excitations? Here I'm only telling you about gluons and so on. Because in the remaining -3 minutes, I would like to tell you a little bit about some cool physics that I think we can extract out of this. Okay? But perhaps what I will do is the following. What do you think? My proposal is the following. Let me summarize with some blah blah, and then those two that want to stay, I can continue for half an hour more and tell you some of the answers to the polemic questions that I said in the beginning. Do amplitudes factorize? Do amplitudes have poles, like Freddy was saying, or is it all a light? So, does it sound good, or do you prefer if I go for 10 more minutes and I just stop there, in case you are destroyed? 10 more minutes and stop, or 1 minute and stop, and then make a small break of 5 minutes, and then we continue with some random comments about what physics we extract. Sorry? Small break? So let me then just conclude for those for which this is a bit out of your range of interest. So the basic idea is that now we have this kind of representation. And what do we want to do with these kind of things? What do we now do with these things? So suppose we find your P's, you have the result, and so on. What can you do in practice with this? So first thing is you have a solution at finite coupling. You can go to weak coupling and you can go to strong coupling and see what happens in both regimes. When you go to weak coupling, you get these pentagons and you expand these functions at weak coupling, like I was expanding the energy and getting these psi functions and so on. You expand them at weak coupling. And what this allows you is you remember when I was saying the Wilson loop is 1 plus e to the minus tau times something plus e to the minus 2 tau times something. Now we can compute these guys exactly, very easily, to any loop order. Okay? And this is being used right now. People that do the most advanced loop computations, like Lance Dixon and collaborators, the way they do them is they don't do Feynman diagrams. They just say, well, at one loop we have logs and Li2s, like I wrote. At 2 loops there are Li4s, Li3s, and so on. So they start getting some intuition about the class of functions that can appear. So then they know at 5 loops I will get Li10, Li9, Li8 with these kind of arguments. And they make an ansatz with like 1,000 constants to fix. Right? Literally, I mean, I think they have literally thousands of constants right now. And then they say, okay, I take this big ansatz and I expand it, Taylor expand it. And then we give them predictions, because we can expand easily. We cannot get the e to the minus 200 tau, that's very hard. But when we expand in e to the minus tau, then that hashtag there is a full function of sigma that I can expand many, many terms. So we can give them 1,000 terms here, plus 1,000 terms here, plus another 1,000 of terms of the next one. And at some point, they fixed all their constants. And then we start sweating, because when they fixed all of them, say, using this one, we check the e to the minus 3 tau. And now it's totally independent check without any free parameters. Either it works, or both, or their guess is wrong, or our integrability bullshit is wrong. And then we do it, and then yes, it works, and it's very important to cross-check, because when I say you solve them, sometimes there are more than one solution, so we need to make sure that we are picking the right one, and we are making the right guesses, and so on. Then we go to strong coupling. Strong coupling, very nice things happen. Like I said, the S matrix is 1. So if the S matrix is 1, you can easily see that you can say that the pentagon is 1. It's a solution. Right? No, 1 is a solution of what I wrote. And indeed, what happens is that the pentagon becomes 1 plus something small. So now when you have a sum of all the elements are 1 plus something small, this is the typical example of something that wants to exponentiate. So indeed, it does exponentiate, and then you recognize some object in the exponent. What should this object in the exponent be? So at strong coupling, I'm saying the result exponentiates this sum, and it becomes exponential. I'll give you a hint of square root of lambda times something. What should this something be? The area of a minimal surface that ends on the polygon that we were studying. And indeed, it does work. But to understand it, there are some puzzles. Because when we want to reproduce the strong coupling result, we want to reproduce the string modes, the fluctuations of the string. Many excitations are the fluctuations of the sphere that have 0 mass. Those are good. Some are fermions. They don't appear in the classical result. It's irrelevant. They have mass 1. There are 2 guys that have mass square root of 2. And there is one mode that you can think of the holographic direction in ADS, this Z mode, that has mass 2. And there's no mass 2 here. So you have to stay after the break if you want to know how to solve this paradox. Perhaps ADS-CFT is wrong. Or perhaps there is a solution to this paradox. Okay, thank you. No, I did not. That's true. Okay, can I write them during the break? And then those that don't want to stay but want the references can ask the ones that stayed for the references. Don't worry. I will not be offended if you all leave. How long is the break? What do you prefer? You can be the Sherman. 10 minutes? 5 minutes? So how much? 5 minutes. Okay.
These S4 observations, your fluxing observations, we're sitting in so in the ASCFT, that's is there a nice interpretation for what the scalar fluctuations are doing, or something in that?
So we are considering a Wilson loop in ADS, right?
Yeah.
And we put nothing in a sphere. Because we put nothing in a sphere, the sphere is empty. Because the sphere is empty, it's described by the O6 sigma model, just the model that describes a string on a sphere, a unit vector on a sphere. Yeah. Unit vector. And what are the massive excitations of a sigma model? They are non-perturbatively generated, and they are exponentially small. And that's why the mass of the scalar was exponentially small. So these excitations, being massless, you might wonder, can they be enhanced? Can it be that that's from coupling, because they become massless, it's not nice to truncate the sum, because now they're very light. So perhaps in some situations I need to resum it. And perhaps because I need to resum, perhaps it will challenge my intuition about the behavior of amplitude in some particular limits. And indeed, it leads to very surprising results, for example, the linear limit of scattering amplitude. So they are very interesting physics, these scalars.
Sorry, Pedro. When you talk about insertions, was it fast? It was precision. It wasn't as fast as the integrability half an hour. When you talk about inserting this kind of insertion properties, what do you really think about the fact that it's set of a huge operator in the CFD with a lot of derivatives and some F?
It depends. Sometimes I literally think take the Wilson loop and put an F on the Wilson loop.
Yeah, that's what I'm asking. So it's the same thing.
The same. If I could, I would just think in terms of the Wilson loop. It just so happens that the integrability techniques are not developed to attack directly in that language. So if I want to compute energy or S matrix or something, I think in terms of local operators. But if I want to study these pentagon transitions or get some intuition about what's happening, I prefer to think in terms of Wilson loop.
Okay, but if I do an insertion on the Wilson loop, then I can ask what is the scale dimension of that guy inserted on the Wilson loop. It's not
That's right.
to me that this has anything to do with the scale dimension of the big operator with lots of derivatives.
Good. So let me just tell you a little bit about a couple of things that I think are kind of fun applications of having an exact solution at hand. A couple of things that we can start asking ourselves. And for that, sometimes I will write expressions without deriving them because, okay, as you see, there is a lot of things. I cannot just say everything. So we have a list of questions that we wanted to understand. And one question we wanted to understand is what happens to a scattering amplitude when we take a subset of momenta, K1, K2s, and K3, for example, and then we have the other ones up here. And what happens when we send K1 plus K2 plus K3 squared to 0? Right? And the question is, what happens when we do it? And what is the naive intuition? The naive intuition based on tree level is that when we do it, the amplitude factorizes and develops a pole where if this is capital P, this is 1 over capital P squared, right? It's what we saw when we were doing BCFW. And that's the idea. This amplitude factorizes into two amplitudes where particle 1, 2, 3 are on one side and particle 4, 5, 6 are on the other side. And this is true at tree level. So this is not a question. This is true at tree level. Okay? So again, we should make this very informal. So please ask lots of questions and so on. It's not a lecture. It's just we are just discussing. I'm trying to tell a couple of things that I find fun. But so first of all, let's note that here, this pole, we have it for NMHV amplitudes, not for MHV. So it's not there already for everything. So let's remember why. Suppose it's MHV. So let's do it MHV. So let's suppose we put plus, minus, plus, I don't know, minus, plus, plus. You see? This has two minus and everyone else is plus. Now this particle here, is it minus or plus? You see, okay, here there is no option. It's immediately, whether it's minus or plus, I have 3 plus and 1 minus only, or 4 plus, it's 0. So here there is even no option. Let's try to make it a bit better. Let's put plus here and minus here. Does it help? Now I can put a minus. This one is plus, plus, minus, minus. But then I have to put a plus here and it's 3 plus. Right, so I'm done. MHV have no factorization pole. So that's known. However, if it's NMHV, so if there are 3 minus and 3 plus, like here, then it works. Because then I can have a plus and a minus. Okay? Okay, good. Probably, yeah. Good, good. Plus and minus. Then there is a pole. Okay, good. So is this something obvious? For example, when we were writing these expressions for MHV, I wrote a bunch of logs and polylogs for MHV. And logs and polylogs don't have poles. I mean, by definition, they can have at most some log singularities. And this was for MHV. It was for the usual bosonic Wilson loop. And I did not tell you anything in these lectures yet about NMHV amplitudes, because for those we would need a super Wilson loop. So that's what I'm going to tell you very, very briefly now. But let me just tell you let me anticipate, or not, let me think. Okay. So the claim is the following. Let me think. Okay, good. So let me write the Wilson loop for the hexagon. And I will explain what this means. So first, one loop hexagon. This is the one we wrote the last lecture. And then I want to write at tree level, but for the hexagon NMHV. And here it was for MHV in the previous lecture. Okay? So I want to write these two expressions, MHV and then MHV. So let me first remind you what this was. This was 1 plus e to the minus tau. Then there was 2 cosine phi. And then there was some function of sigma, which was 2 sinh sigma times sigma minus 2 cos sigma log of 2 cos sigma. Okay? And if we do it, and all this is times g squared, this is a one loop effect, plus dot dot dot. And now I will explain what this object means, but let me already anticipate the result. The result is 1 plus e to the minus tau plus I phi, no cosine, but just one exponential, times 1 over cos of pi sigma, times g to the 0, it's 3 level, plus dot dot dot. So this is how they start. Okay. Okay. So first, the idea is the following. There exists a super Wilson loop which we define as saying that we take the amplitude and divide by the amplitude at 3 level for MHV, but only for MHV. So when we do it, this object becomes our bosonic Wilson loop, our MHV Wilson loop that we have been discussing, plus, and then there's a bunch of Grassmann variables that tell you what NMHV amplitude you are considering. For example, we can have eta 1 to the power 4, like Freddy was doing, times some amplitude for some NMHV polygon, plus dot dot dot. Okay? Where these etas are Grassmann variables, you remember that MHV had 8 etas because it was 4 for one gluon of positive helicity, 4 for another gluon of positive helicity. And if it's NMHV, you need 12 etas, and we divide by 8, so there are 4 more. So these guys start being no etas, 4 etas, 8 etas, and so on. And this notation, 1 to the power 4, could mean that I take my Wilson loop, and in the supersymmetric version of this Wilson loop, what I do is on edge 1, say, I put here on this edge, there is a super connection that is A plus eta 1 times some fermions plus dot dot dot. And what I do is I compute my super Wilson loop where they have some etas along the edges, and these etas are Grassmann variables. So what I'm saying is that I am expanding them down by default, and I pick the guys that have 4 etas on this edge. Okay? This is the super loop. There exists such object which is the super loop. You see, someone asked me at some point, you asked me, right, whether it was a super loop, and I said no, and it was correct. This is not a supersymmetric Wilson loop, in the sense that this object, I expand and I bring down 4 fermions. So there are 4 fermions and a flux tube with 1 million gluons. It's not supersymmetric. The gluons win. Okay, but indeed, people call it a supersymmetric Wilson loop. So what we are doing here with the super Wilson loop is saying that I put something on this edge. And what is this something? I don't know. I don't care. This is the beauty of this method, but it has 4 etas, so it is a singlet of our charge. So from the point of view of understanding what can flow on this Wilson loop, the analysis of the excitations, it's the same thing as before. It can be an F, it can be 2 Fs, it can be a psi and a psi bar, but it cannot be just a single scalar. Okay? So everything is the same as before. Okay? So everything is the same as before for this object, so how come the result is different? Right? How come the result is different? If everything is the same as before, if I would start deriving it using integrability and so on, what would change? And what would change is the following. There exists 0 modes of the bootstrap. You see, you could see this as a bug, because you'd say, oh my god, I have more than one solution, it's a pain, how can I select the solutions? But it's a feature, because it better be that I can describe all possible amplitudes, not just MHV amplitudes. So the fact that there is some freedom in the way I solve my bootstrap and that there are more solutions, it's a good thing, because it allows me to describe some pentagons that describe the first line and some pentagons that describe the second line. But of course, it should not be something crazy. It should be something simple, the ambiguity freedom. And it is. So let me tell you what it is. Note that what happens when I take I said that this is what this u gamma means. I take this and I go through these cuts. So this, another way of saying it, is that this is under this gamma, x plus minus go to 1 over x plus minus, where x plus minus are the so-called Zhukovsky variables, which are defined as x of u plus minus I over 2, where x is defined as x of u equal u plus square root of u square minus 4g squared over 2, which is equivalent to defining as x plus 1 over x equal u over g. So you see there are two solutions, x and 1 over x, and when I cross the cut of this square root, I flip the two solutions. Okay? So crossing this cut that I drew there is nothing but taking these functions and flipping them from x to 1 over x. Okay? Good. Now, we note something nice. We note that, for example, if p0 to u, for example, is a solution, okay? So suppose we have pf and pf bar 0u. So these are two solutions. For example, we normalize them to 1 in the case of MHV. Right? So this was just equal to 1 for MHV. We said we normalize these guys to 1. Right? 1 obeys what kind of nice axioms? 1 obeys the axiom that if I take 1 and carry it and do 5 analytic continuations, I get 1. Right? Is it clear? So 1, I do 5 analytic continuations, is still the function 1. But what should it be the most general case? What I should have is that, what I need to have is that pf of 0, and if I do 5 gammas, u to the 5 gamma, this should be pf bar of 0u. Right? And by the way, this is not true. What I wrote here, this is not this. 1 second. So u is approximately g. So it's like this. Okay? And this is x plus minus goes to g squared over x plus minus. Okay, so in other words, if you want, g over x plus goes to x plus over g. The quantity that flips is g over x plus. It's kind of a detail, but it will be a bit important soon. So this is the kind of thing that we need to satisfy. But this kind of property, you see, it's very simple. If this is a solution, if I multiply this guy by x plus x minus over g squared, and multiply this guy by g squared over x plus x minus, this is another solution. Right? Because what happens? Each time I do a crossing, this factor flips, by definition. So p goes to p bar each time. And when I do 5 times, p goes to p bar, indeed. So this is also a solution. So I should be careful that sometimes I might need to put these factors of Zhukovsky variables in my solution. And these factors, they have a couple of funny things. So first, at weak coupling, they are very simple. It is just u squared plus 1/4 over g squared. So perhaps I can just go to weak coupling and see if such factors are there. I just look at the data, at experimental data, and I see, do I see these factors or not? But the second thing we note is that they have an important physical effect. They divide by g squared. So they are enhancing loop order. And these ones, they multiply by g squared. So they are suppressing loop order. Right? But okay, but this is good because you see, this effect shows up 1 loop earlier compared to that one. Okay? Good. So now you have these two functions, and you ask yourself, what are the Fourier transforms of these two functions? And the Fourier transform of this function was mu of u, which was 1 over cosh of pi u times u squared plus 1/4 times g squared. And now, what is the Fourier transform of 1 over cosh? You remember, that's why I prepared this example, of course. Everyone knows Fourier transform of 1 over cosh, by the way, there's no pi here, sorry, is 1 over cosh of pi u. What do they differ by? Exactly u squared plus 1/4 divided by g squared. Okay? Exactly the kind of form factor that we said we could. So then we conjecture, okay, this is all there is. There is this beautiful thing that MHV and NMHV to all loop orders, the only difference we conjecture is you just put these simple Zhukovsky vectors, x plus x minus over g squared. Okay? Now, what physical consequence does this have? It has an important physical consequence, which is related, which we can see very easily in position space here. We see in position space that there's something happening when sigma goes to I pi over 2 here. It explodes. Right? This gives a pole when sigma is I pi over 2. It does not? Yeah, it does. Cosh of I pi over 2 is cosine of pi over 2, which is 0. What about here? Here, no. When sigma goes to I pi over 2, it's log of 0 times 0. It's okay. It's 0. So one has a singularity when sigma goes to I pi over 2. The other is not. The other does not. So what is this point sigma equal I pi over 2? This is the factorization point, exactly. So let's see that. So we take our polygon, okay, and we have u2, the nice cross ratio, which is the one I always write. I never write the other ones because they are very ugly. This is what u2 is. But can someone look at the notes and tell me what u3 becomes when I take tau to infinity? You remember, u3 is a function of tau, sigma, phi, and so on. What happens when I take tau to infinity? So u3 when tau goes to infinity. Good. So it becomes nice as well. So let's write it as well. Okay? So what was this u3? What was this cross ratio u3? It was just the rotation of u2. So let's remind ourselves what u2 was. u2 was this distance times this distance over this distance times this distance. Okay? So u2 going to 0 means this is very big, or these points become null separated. And now u3 you just rotate, and you rotate and you see this dashed line moves here. Right? Now it's just rotation by 1, cyclic rotation. So u3 going to infinity, which is what happens when sigma goes to I pi over 2, can be thought of as saying that these points here become null separated. Right? So in other words, we can flatten first, and even after flattening, we still have freedom to play with sigma and go to the factorization limit. Which is very nice, because it means that this approach, that is designed for tau very large, can nevertheless still tell us things after the factorization limit. It's not like we have to resum many things. We can access it within the factorization, within these stretched polygons, right? So I can flatten and then tune sigma to go to the dangerous point. Okay, good. So we understand that when tau is much bigger than 1, and then sigma goes to I pi over 2, this is what we want to analyze. This is the factorization point. Right? Good. Okay, great. And indeed, we see this guy as a pole, and this guy has no pole. Okay, but this is leading order in perturbation theory. Let's not draw conclusions too fast. But okay, people that do perturbation theory will be happy with this conclusion. How do we see it in a language closer to the OP? How do we see this language in the language of this OP, of pentagons, and so on? Sorry? We could also do n squared and so on. That's the claim, yeah. This is something we understood 4 days ago with Lucy and others. So, but I think it's true. We might have to do some checks, but it's true. We cleaned up 5 days ago. 3-level NMHV. N square MHV x again is equal to 1. Okay, because N square MHV it's equal to MHV, sorry, not equal to 1. It's the same as MHV because N square MHV is the same as MHV bar. Okay, but good, but let me come to that point. Because you see here what happened. I forgot to point this out. What's happening here? What's happening here is that you see, you get cosine of phi upstairs and just phi downstairs. Right? Why? Because you should put x plus x minus over g squared for the positive helicity and g squared over x minus x plus for the negative helicity. So the negative helicity is delayed. So what we are saying is that if you want to find a negative helicity guy in NMHV, it's delayed. And all this makes sense because you see, here what we are doing is we are putting stuff by hand on the Wilson loop. So we are helping create gluons because we are inserting stuff. Right? So you insert stuff with the quantum numbers of a gluon of positive helicity. So it enhances. So we put stuff with the quantum numbers of a gluon of positive helicity. Good, it wants to be created. But the guy of negative helicity, first you need to annihilate this gluon and then produce a gluon of the opposite helicity. So it's delayed in perturbation theory. Whereas before it was a one-loop effect. So it enhances some processes and delays some other processes. So we could predict what is the result that appears for NMHV. The first time that e to the minus I phi will appear will be at 2 loops. So you can already predict this. If you do a computation at 1 loop, you don't find minus I phi yet. Yeah. In 45 minutes. No? People have to wait. That's a detail. Okay, people are warned about that. Very good. So let me at least go 5-10 more minutes just to finish this factorization. Sorry? Yeah. That's right. We could also all go for dinner downtown if people are interested. Very good. Do you want to go downtown? We could go to this pizzeria. There is a nice pizzeria. We could all go. Very good. We can change the schedule for tomorrow even. You can start later. Sorry? Yeah, this pizzeria indeed. Yeah, we should reserve this other. Anyway, we can decide in 10 minutes. So, where was I? Okay. So this will not take much longer now. So, what do we have there? We just have some integral of some measure for the gluon. Sometimes some factor, some extra factor, let me call it h of u. H of u is this g square, is this x plus x minus over g square. So we put it or not put it. So this is 1 for NMHV and 0 for MHV. And then we have e to the 2e to the I p of u times sigma minus, okay, yeah. So we have this in general. And now what are we saying here? What we are seeing is that you see that what is happening is that this term at large u, it behaves as e to the 2iu sigma. And this measure, because of this 1 over cosh, this measure at large u behaves as e to the minus pi times u. So you see that as long as the imaginary part of sigma is not too big, we are good, and it converges. But what we should start being worried is when sigma approaches I pi over 2. If sigma approaches I pi over 2, this starts to be dangerous, or minus I pi over 2. Right? I mean, pi over 2, it's dangerous for minus infinity. Yeah. We can say minus I pi over 2. Okay? So sigma equal minus I pi over 2 is dangerous. And indeed, in the examples we considered, we see very well what happens, which is that for NMHV, the second line, we have no factor to compensate. And when we go to this point, indeed, we develop a pole. But for MHV, we have this extra 1 over u squared suppression at infinity that still makes it okay when we go to sigma equal I pi over 2. So even if you go there, you still have 1 over u squared suppression, and you are good. Right? You agree in this example? Just by looking there. Now, what happens if we try to do NMHV, but not at leading order in perturbation theory, but at all loops? Okay? So what does it mean doing it at all loops? It means that you have to go to the expressions that I wrote in the beginning with this matrix kappas and these kappas of u's and m's and so on. And what you can see is that what happens is that the behavior is roughly of the form. What happens is that this measure, mu of u, goes as e to the minus pi u from the cosh that is in front, which is the analog of these gamma functions in front. And then there is minus the cusp anomalous dimension. This is schematic. There is another term, but I'm going to write only one term, times log square of u. Okay? So what, and the momentum goes to 2u at large u. This is large u, but finite coupling. So what I'm lying is that there is also a log here, but the log square is what's important. Okay? So you see something funny what happens, which is, if I expand in perturbation theory, and I bring this f down, then it looks like I have a pole. Because I expand f down, and what is happening is that I have a toy model of the following form. The Wilson loop is governed by e to the minus tau, some integral du, the relevant part is at infinity, so I have e to the xi times u, e to the minus xi times u, minus f of lambda times log square of u, where xi is how far I am from this point. It's sigma plus I pi over 2. Or maybe minus that, I don't know. Okay? Right? As I'm approaching that point. So you see what's happening. If I take out this, and I compute this integral, it's 1 over xi. It's a pole. Right? What happens if I expand this down? I get integral e to the minus xi times u times powers of logs. So what happens in perturbation theory, at L loops, it will look like a pole. It will be 1 over xi, which is the famous BCFW pole that factorizes. And because of bringing down logs, I just get some log enhancement. Okay? But now we understand the fates of these logs that we see in perturbation theory. What's the fate if I resum all these logs? And if I take this expression but don't expand, take it at finite coupling? What happens if I put xi equals 0 here? I put xi equals 0, nothing happens. This integral is convergent. So there is no pole. So this factorization thing is a lie. Amplitudes do not factorize at finite coupling. And it's not surprising. I think it's very useful to have an explicit example. But once you see the result and then you go and try to understand the physics is clear. The point is, what is the probability of forming a single gluon in the intermediate channel? Well, that's very small, because the gluon can also go with a very soft gluon together with it. And then 2 very soft gluons, and then 3 very soft gluons. So what's happening is that the probability of finding just one gluon that gives the pole is exponentially small. So the probability, when we compute the gluon, and the gluon is coming alone, this gluon comes automatical with e to the minus some cusp anomalous dimension, which I call in these lectures f of lambda, times some infrared divergence, some suppression, with how far we are from the factorization point. And because of that, the probability of just of getting this pole, which is of getting this single particle, is actually going to 0. So what happens is that when you are studying this factorization, you say, I keep these diagrams, and I keep these diagrams, and so on, because they have this pole explicitly here. And I drop the other diagrams. I drop the diagrams where I have 2 particles here and 4 here, because they have no divergence. Right? But this is actually the opposite of what you should do, because these diagrams are the ones that are going to be dressed by an exponentially small infrared suppression, and these ones are the ones that will give an order 1 contribution. So if you just sit at the factorization point, these are the diagrams that give you what the final result for the amplitude is. And these ones, they will come dressed by an exponentially small contribution. They will just vanish and go to 0. Now, of course, what happens is that if you are at very, very, very weak coupling, the intuition before should be okay. We still have particles, right? What we are seeing here is that as we go to strong coupling, this notion of particle is not very meaningful, because we have a particle plus a soft gluon plus 2 soft gluons. It becomes more something of shell, more like a jet. And it's this off-shell process that is removing the singularity. It's the statement that, say, at strong coupling, the notion of fundamental gluons stopped making sense. But of course, at any finite coupling, you see something that looks like a pole, and then there it's cut off, but you will not see this thing being cut off for practical purposes. No, at strong coupling, then it's totally different. Then it's really totally washed out. There's no notion in which there is a pole in some sense or something. It just, there is not. That's right, but the way you see it, but okay, that's right theoretically, and indeed, the way you see this thing is when you start doing perturbation theory at weak coupling and you start seeing these logs that are telling you that you want to, in fact, that you will infrared suppress. But of course, in experiments, we do see bumps. So. Moral is the same thing. Moral is the same thing. Once you see it, it's not very surprising, but I think it's very good to have an explicit example where we understand the math of what's going on. And finally, the math is very simple. It's all about this integral, e to the minus psi u minus log square. You put psi equals 0, it converges. You expand, it doesn't converge. It's a very simple time model that I think shows in a very, very explicit way what's going on. But about strong coupling, this was something that was puzzling us for a while, because when people were saying amplitudes factorize, then there was this puzzle because the amplitude, the area at strong coupling, is the same for MHV and then MHV. This area contribution should be universal. So what are we saying? This was what we were confused about. We said, do people want to say that this hexagon, that a new line will appear and this will become 2 separated surfaces? Just because these points become no separate. It's a very, very drastic effect. Suddenly the surface decides to go to the boundary. Why not? It could be. These points become no separate, the very fast particle is generated, and the surface just goes to the boundary. But it was hard to believe. Why would it happen for MHV and not for an MHV? It was not very intuitive at all. Then we really tried to find this order of limits. Perhaps there is an order of limits issue if these points are closer than the coupling is and so on, but we could never find it. But perhaps we still have to look harder. But I think the simplest explanation is that there is just no factorization. And there are some statements in the literature which are similar to this about correlation functions becoming Wilson loops and so on that I think are a bit erroneous, and that the correct intuition is that some dualities simply are, strictly speaking, not realized about concerning amplitudes and Wilson loops in the strict sense for the same reasons. So let me just end with one sentence, because I think it's something very cute, which is that, as we said, 2 of these gluons, if we follow these expressions to strong coupling, they have a sharp interpretation. They are 2 of the modes of the string. But the string in ADS5 has 3 modes, because the ADS5 is 5-dimensional, so we have 3 transverse modes to the string, right? Where is the third mode? Where is the third mode of the string? So we have the 2 Goldstone bosons, which are the F and the F bar. Where is the third mode in ADS? The third mode in ADS comes from a bound state of 2 fermions. I find it very interesting that this is the way this holographic direction is realized, is these 2 fermions. They don't like to bind at finite coupling, but at strong coupling, they more and more and more, and exactly at strong coupling, they like to form a bound state of mass 2, and this is where this mass 2 comes about. And this is, if you want, a very, very concrete example of this blah blah of emergence of space-time and so on. Here you can see it extremely concretely. If I had time, I would do it, finding that these fermions form a bound state and they become a mass 2, and this is how this holographic direction emerges. I think it's really cool. Okay, very good. I think it's enough. I converged. Are you happy? Okay, so that's I'm going to it. So remind me what we did. So we started with Wilson loops, right? General stuff about Wilson loops. So for that, I don't think there is a reference. Just Google. I mean, it's or Peskin or something. For the first lecture, it's just very general. Then the second lecture, lecture 2, is based on an appendix of a paper we wrote, which is the appendix of 13062058. So this is about geometry. Also, okay, this is about geometry. Then lecture 3. Lecture 3 is about this ferro and antiferro. You can see a review by Fadev, which is called How Integrable Model. I forgot the rest, but from the beginning of the title you can see. Not everything I did was there. Basically what I did, I took this review, and there were many things that he did not finish that I finished, but the review contains many more things that I did not do. And finally, so today, lecture 4. So the main picture of these pentagons and so on, of saying that we sum over pentagons, this is a very short paper, so if you want to see, it's a very short paper we write. It's 4 pages. You can maybe start from this one if you want to have a general picture. That we wrote in 13. That's his main picture of these pentagons. Then, what did we go from there? The gluon story. So, gluons is in a paper that you can find with a similar title. Okay, I can tell. About gluons. And you